Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series delivered for the BSc Physical Sciences course. The paper is on Applied Electronics. This is semester 4 and we are going through the unit 2 where we started with the positive ray analysis. Now we move on to Bainbridge mass spectrograph. The contents of this lecture are identifying isotopes of helium and neon, etc., concepts of mass numbers, Bainbridge mass spectrograph, which is better than the Aston's mass spectrograph, which is due to obviously Aston, a student of Sir J.J. Thomson, the man who discovered the electron and investigated the positive rays, which led to the idea of isotopes and so on. We discussed in the previous lectures about positive rays. What are positive rays? Positive rays are made up of positive ions. If you have air and you have got hydrogen, and the positive rays, as I told you in the previous lecture, they are made up of ions of hydrogen atoms. What are the ions? Now we know the ions of hydrogen atoms are nothing but protons. So you have got protons going in a particular direction. They are called the positive rays. And I told you again, in the case of hydrogen molecule, if it is ionized, you will be having the hydrogen ions, and so the specific charge, suppose you say E by m as a specific charge, and the mass comes in the denominator. Suppose the mass comes in the numerator, the mass of the hydrogen molecule. When the hydrogen molecule is ionized, you have got 2 protons. So the E by m value will become twice. That is what you find here. When it becomes ionized, 1 electron is lost, producing the positive charge on the ion. Hydrogen molecule becomes a hydrogen molecule ion, but its mass is twice that of the hydrogen atom. That means the hydrogen molecule contains 2 positive charges. I mean, we now know they are the protons. Hydrogen molecule is made up of 2 hydrogen atoms. When 1 electron is knocked out, it becomes a hydrogen ion, but still the nucleus contains 2 protons. This means the specific charge of the ionized molecule is half the specific charge of the ionized hydrogen atom. If E by m is 1 by 2, or m by E will be 2 times. Okay, the mass comes in the numerator. encouraged by these experiments, Thomson tried putting helium in the tube. Suppose you are having helium, then what will happen to E by m? That is the charge to the mass ratio, and managed to obtain a third line. Every line corresponds to a particular mass with a charge equal to 1/4 that of the ionized hydrogen atom, because helium contains what? 2 protons and 2 neutrons, as we know now, because the mass of the proton is almost equal to the mass of the neutron. So the mass of the hydrogen atom or the mass of the proton will be 1/4 the mass of the nucleus of the helium atom. That is the reason why if you take helium atom with a charge to mass ratio 1/4 of the hydrogen atom, that means the mass of the nucleus of helium atom will be 1/4 that of the hydrogen atom, because helium contains 2 protons and 2 neutrons. So the mass number comes into the presence. So mass number is the one which refers to the masses of neutrons and masses of the protons. So those ideas come into the picture after the work of Thomson and Bainbridge. Now know that helium nucleus contains 2 protons and 2 neutrons, which are uncharged particles. Of course, neutrons are uncharged. That is the reason why you got 4 here. The nucleus of helium is 4 times more massive than that of the hydrogen. So the ratio of the singly ionized atom is 1/4 the size. This gave Thomson his first evidence that positive charge could be carried by something other than hydrogen. Hydrogen alone will not give positive rays, but you can have positive rays of hydrogen molecule. When you knock off one of the electrons, you got the hydrogen molecule becomes an ion. Thomson created better vacuum in the tube and found that he could get parabola for other gases. As I told you, not only hydrogen, you can have hydrogen molecule, then you can have other gases like nitrogen, oxygen, carbon, and so on. Thomson numbered the trails in relation to the mass to charge ratio, or charge to mass, or mass to charge ratio of the hydrogen ion. The ionized hydrogen molecule is 2 on this scale, because hydrogen molecule contains the mass is twice that of the hydrogen atom. Since it carries the same charge as the hydrogen ion, but is twice its mass. The helium, on the other hand, will have 4 on this scale. Okay, these numbers are the atomic mass units, and we now know that they are the number of neutrons and protons contained in the nucleus. At the time these measurements were taken, the atomic mass scale was defined by giving oxygen a common isotope, an exact value of 16 atomic mass units. This definition got changed in 1962, and now we have carbon as the atomic the mass number of carbon as 12 atomic mass units. That it becomes the standard. That is what you are having now. Each kind of charged particle produced its own parabola. So depending upon the mass, you have the parabola. It will be hitting the photographic plate at different points. Okay, depending upon the mass. It seemed that any gas could be made to carry a positive charge. Any gas, nitrogen or oxygen or helium. Thomson realized that by measuring the tracks on the photographs, he could tell what type of gas were present in the tube. So it can be used as a gas analyzer. So as I told you in the earlier lecture, from physics you pass on to chemistry, and so the discharge tube which was used by Thomson in determining E by m of the positive charge, E by m of the positive rays, it can be used as a gas analyzer, because every gas that you talk of, neon or helium or oxygen, nitrogen and so on, they have got, because the masses are different, the E by m values will be different. Therefore, the parabola will hit at different points on the screen. So it can be used as a gas analyzer. So this is what I am having here. his apparatus provided a method of chemical analysis. So from physics he passed on to chemistry, from chemistry he passed on to biology, and from biology passed on to medicine, and so on. Therefore, this area is of immense importance. So Aston joined Thomson in the Birmingham University. They together improved the accuracy of Thomson's positive ray apparatus. So they investigated neon. The important point is neon has got a mass 20, and there is another trail for neon. They got two parabolas. Okay, one corresponding to 20, but this trail is always accompanied by a second trail at 22 and a very weak one at 11. So could this trail be due to a molecule? Two atoms of hydrogen bound to a single neon atom would measure 22 on the scale. So they proceeded to determine why there are two traces in the case of neon, and you find that there are two isotopes of neon. The two isotopes of neon are chemically identical because the number of electrons are the same. Neon has got how many electrons? You've got 10 electrons. So the properties are decided by electrons only. So the chemical properties will be different, but the number of neutrons that will be having will be different. If you've got 10 electrons, there should be 10 protons, right? But the neutron number will differ. Therefore, you got neon 20. When 20 means what? 10 protons and 10 neutrons. 22 means obviously 10 protons and 12 neutrons. They both have a nucleus with a positive charge, 10 times the mass of the, 10 times the size of the charge on an electron, and they both have 10 electrons in orbit around the nucleus. You've got 10 electrons, but the number of protons will be different. Therefore, the concept of isotopes, what are isotopes? Having the same atomic number. You got the number of electrons will be equal to the number of protons, but the number of neutrons will differ. So the weight will, the mass number, weight will be different. The trace at 20 was ionized neon as expected, but the trace 22 was also ionized neon. So you got two different neons. The two types of neons were chemically identical, but their masses were different, right? That means what? One of them having 10 protons, 10 electrons, the other has got 10 protons. I mean, all of them should have 10 protons, but the number of neutrons is in one case is 10, the other case is 12. The trace at 11 was the second type of neon which has lost 2 electrons. Isotopes were studied by Saudi in Canada, but this is the first demonstration that a non-radioactive element could have isotopes. The radioactive elements showing isotopic effect was studied by Saudi, but this is the first time that element like neon, which is non-radioactive, which could have isotopes. So many scientists were skeptical about the forms of neon. Aston, a researcher working in the Cavendish, set out to separate the two forms. His work was interrupted by war and so on. Anyway, it was established that the Aston developed the first mass spectrograph to show different isotopes on strips of photographic film in the case of neon. So that is the first mass spectrometer that is due to Aston. His work was followed by Bainbridge. Now I'll pass on to the Bainbridge mass spectrograph. Let us have a short break at this point. Welcome back to the break. Now we have been discussing about the isotopes. I told you about the fact that positive rays are nothing but ions of hydrogen atoms. Ions of hydrogen atoms are nothing but protons. Then we pass on to hydrogen molecule. You knock off the electron. Then what you have is you have got 2 hydrogen atoms minus 1 electron. But the mass number will be different, because the hydrogen atom you got only 1 proton. Now you got 2 protons. Okay, so the mass number will be different. You got the mass becomes heavier, twice that of the hydrogen atom. Then you go to the case of helium, wherein you got 2 protons and 2 neutrons. So the mass number becomes 4. Then we discuss about the case of neon, where we have 10 protons and 10 electrons. Obviously, the atomic number of neon is 10. So the number of electrons should be equal to the number of protons. 10, the mass number is, in the first case it is 20. We have 10 protons and 10 neutrons. Then the helium, in the case of neon, you have 2 isotopes. One is 20, the other is 22. I showed the animation for the case of neon. You got one neon with 20 mass number, the other has got 22. The concept of mass number, the isotopes, they come from these studies which are done by people like J.J. Thomson, Aston, Bainbridge, and so on. Okay, Soddy talks about much earlier he found isotopes of radioactive elements, but these are isotopes coming from non-radioactive elements. And we now discuss the Bainbridge mass spectrograph. I told you the mass spectrographs went into the hands of chemistry people, because depending upon the gas present in the discharge tube, the parabola, which I showed in the last lecture, the deflection suffered by the charged particles or the charged ions, depending upon the mass, the point where it hits will be different. And I will show the value of R, the magnitude by which the ion has been deflected. All these things will come from the Bainbridge spectrograph. So we pass on to the Bainbridge mass spectrograph. In this form of mass spectrograph, a velocity selector is used, which allows a beam of positive ions having the same velocity to pass undeviated through crossed electric and magnetic fields. This is a velocity selector, the same velocity to pass undeviated through crossed electric and magnetic fields. If X is the intensity of the electric field and B the magnetic flux density, then the force experienced by an ion of positive charge E and velocity V will be Xe. Xe is the force experienced by the electron with the electric field of strength X, whereas BeV is the force experienced by the electron because the magnetic field of flux density B, BeV. So these are the two important expressions. If these two forces act at right angles and in the same plane, the ion will travel undeflected. Here B is mu naught times H, where mu naught is the permeability. From the figure that I will be showing here, X is the intensity of the electric field acting in the direction PQ in the plane of paper or the computer. The magnetic field or the flux density B is perpendicular to the plane of the paper or an inverse. The electric field will deflect the beam downwards and the magnetic field will deflect the beam upwards. You have to use the Fleming's left-hand rule, thumb rule. You want to know how your charged particle will move, or the force experienced by a charged particle when you apply a magnetic field of strength B and the electric field of strength X. As I told you, one of the fields tries to move it in a particular direction. The other field, the magnetic field, tries to put it in the opposite direction. So force experienced by the ion due to the electric field is Xe. Force experienced by the ion due to the magnetic field is BeV. If these two forces are equal and opposite, right? Equal and opposite, then xe will be equal to BeV, or velocity v will be equal to x by be. Therefore, thus all ions, this is a very important expression, thus all ions having a velocity v given by x by be do not suffer any deviation while passing through the crossed electric and magnetic fields. This is a Bainbridge Morse spectrograph. You got an anode here, the massive particles are passing through an electric field, and the magnetic field is applied perpendicular to the diagram. You got a diagram here, you apply the magnetic field along this direction. The electric field, you got in this direction. You got the positive ion beam is coming here, the positive rays or positive ion beam is coming here, and depending upon the masses, M2 is greater than M1. So M2 will undergo a larger deviation. So M2 will be found here. It will be hitting the photographic plate here, whereas M1, M2 is greater than M1. The lighter mass will come here, whereas the heavier mass will go here. Okay. So you got a slit here, S2. Essentially, a positive ion is moving through an electric field and a magnetic field applied perpendicular to the plane of this diagram. So when you have a positively charged ion subjected to both a magnetic field and an electric field, then the ion will undergo a deflection as shown in the diagram. You got a vacuum chamber, the electron beam, you got a cathode and anode here. The two electrodes are here to build the electric field, and the applied magnetic field is perpendicular to the field direction. What I showed you here. So these things are described here. All the ions having the same velocity v is equal to x by b enter the analyzing chamber, and the flux density is given here. The influence of this field is over a semicircle of radius 20 centimeters. So the most important thing to be considered is the following. All the ions having the same value of E by m. I will read again. All the ions having the same value of E by m traverse a semicircular path of radius r, whose value is given by r is equal to mv by b prime e. So how do you get the expression? So this mv square by r will be equal to b prime ev, right? mv square by r will be equal to b prime ev. From this you can determine the value of r. R will be equal to mv square by b prime ev. So you can cancel this v square with the v here. So you are left with v in the numerator, mv divided by b prime e. So that gives them r, the radius of the semicircular path. This is a semicircular path which you have here. This is 2r, right? This is the diameter of the circle. So this is a semicircular path. The magnitude of semicircular path will be given by an expression of this kind. Since b prime, the applied magnetic field, and v are constants. What is v? Because you are using a velocity selector. All the ions of the same mass will be traveling with the same velocity. So velocity is constant, b prime is constant. So because these things are constants, all ions will have same r. Okay, that is a very important point. So the ions having the same value of E by m are focused onto the same line. So all ions having the same mass will be found at a particular point, will follow a particular parabola, and will fall here. M1 will fall here, M2 will fall here. Okay, this is what I am trying to tell you now. Ions with different values of E by m are focused on different positions on the photograph plate, obviously. Ions with different values of E by m will fall at different points on the photographic plate. From the equations, it is clear that the radius of the circular path of an ion is directly proportional to what? The mass of the ion and the constant k. Thus, the spectrograph gives a linear mass scale and is directly proportional to mass of the ion. Okay, the semicircular path. Let us look at the expression again. You got R is directly proportional to M. So the radius of the semicircle, right, it depends upon M. When if it is M1, the track is found here, the trail is found here, or the path traversed by this ion with mass M1, whereas the mass is higher, it takes a different path. The value of R is different, right? Now 2R becomes larger for M2, whereas 2R becomes smaller for M1. So R is directly proportional to M. That is what I am trying to tell you now. Or the radius of the semicircular path R is directly proportional to M. That is what I am emphasize here. Thus, this spectrograph gives a linear mass scale because your mass comes in the numerator, R also comes, is directly proportional. Both of them are proportional to each other, which is an advantage in comparison to Aston's mass spectrograph. After Aston was the first person to make a spectrograph, Bainbridge mass spectrograph is superior to that of Aston's mass spectrograph. The convenience is, as I told you just now, this spectrograph gives a linear relation or a linear mass scale, which is an advantage in comparison to the case of Aston's mass spectrograph. In Bainbridge mass spectrograph, the source is a discharge tube fitted with a rod anode and perforated cathode. Gas is admitted through a side tube, and the potential difference between the anode and the cathode is of the order of 20,000 volts. Many elements were studied by Bainbridge, and in many cases, the results obtained by Aston were confirmed. A number of parallel line images are obtained on the photographic plate. The number of lines corresponding to number of isotopes present in the gas or element. The number of lines that you get refers to, because when the mass changes, the track will change. Thus, a mass spectrum is obtained. Depending upon the mass, the tracks, I showed you that mass M1 falls at a particular point, M2 falls at a different point. By the study of comparative intensities of the lines, the relative proportions of the isotopes, right, can be obtained. So, two things, depending upon the mass, the R value will be different. Then the intensity shows the abundance of the isotope. So, let me now pass on to the summary session of this lecture, which goes as follows. The specific charge of the ionized hydrogen molecule is half the specific charge of an ionized hydrogen atom. The nucleus of helium is 4 times more massive than that of hydrogen. So, the ratio of a singly ionized atom is 1/4 the size. The two types of neon were chemically identical, but their masses were different. From the equations which we saw in Bainbridge's spectrograph, it is clear that the radius of the circular path of an ion is directly proportional to 1, the mass of the ion, and 2, the constant K. Thus, the spectrograph gives a linear mass scale, which is an advantage compared to the Aston's mass spectrograph. Now, we will pass on to the few questions that we have with regard to this lecture. What are mass numbers? Give the isotopes of neon. Give the expression for the radius of the semicircular path traveled by the ion in Bainbridge's spectrograph. With this, we come to the end of this lecture. Now, having discussed more about the discovery of the electron by J.J. Thomson and determination of specific charge by, again, Thomson, it is E by M, we should know how the charge itself is measured. The charge is measured by Robert Millikan, and in the next lecture I will be talking to you about the laborious work done by the famous Millikan's oil drop experiment. With this, we come to the end of this lecture. Thank you.